So we derived the energy balance equation for closed systems, right? And so all it is we have delta U plus delta EK plus delta EP is equal to Q plus W, where the left-hand side here, all the values are their final minus the initial value states. And then on the right-hand side, we're dealing with the energy transfer terms. And so here we're looking at the input minus the output, all right? And I want to emphasize that this is for closed systems. And so for a closed system, that means that we do not have any mass that's crossing the system boundaries. But even though mass is not crossing the system boundaries, we could still have energy cross the system boundaries. Right? And so here's the fundamental energy balance equation that you should write whenever you're dealing with closed systems. All right? But based on the system that you're trying to analyze, there are some terms that you don't really need to consider. And so in this video, what I want to do is try and highlight some key words that you should look out for that will help you simplify terms in your energy balance equation. Okay? Now, let's go from left to right. Okay? And so let's consider the cases where your change in internal energy is going to be equal or about equal to 0. Okay? And so a lot of times you could basically just consider your delta U term to be equal to 0 if there's no temperature changes in your system. Okay? Or if there's no phase changes, no reactions, and if P changes by less than a few atmospheres. Okay? Alright, and the reason why you could assume that delta U is basically 0 there is we have to remember internal energy is describing the processes that are going on at the molecular level, atomic level, and subatomic level. Right? And those processes are affected by changes in temperature or, the phase of matter or reactions, or if how pressurized the system is, right? And if none of those things here are changing, that means at the molecular level that we don't really have any changes going on either. So that means that the internal energy of our system in the final state is about equal to the internal energy of our system at the initial state. Okay? So in those cases, if we don't have any changes in those variables, our delta U is going to be about equal to 0. Okay? For kinetic energy, this will be equal to 0 if the system isn't accelerating. Right? Because if there's no acceleration, that means there's no change in velocity. Right? And if the velocity and mass are the same at the initial and final states, that means that the difference in the kinetic energy is going to be equal to 0. Right? Similarly, the change in potential energy will be equal to 0 if your system stays at the same height throughout the entire process. So if the system is not rising or falling. All right, so those are the energy terms. Now for the energy transfer terms on the right-hand side, Q is going to be equal to 0 if the temperature of your system is equal to the temperature of your surroundings, all right, or if the system is perfectly insulated. Right? And the reason for that is we have to remember that heat is the type of energy transfer that's thermally driven, right? So it's driven by differences in temperatures between the system and the surroundings. If that difference is equal to 0, that means that there's no what we call driving force for the energy to move from one place to another, right? And so thermally, there's no driving force, so Q would be equal to 0. At the same time, if it's not possible for energy to transfer from the surroundings to the system because there's some sort of insulation going on, that also means that your Q is going to be equal to 0. Okay? And I just want to remind you that whenever you see the term adiabatic, all that means is that your Q is equal to 0. For work, this term can be considered to be 0 if your system size is not changing. There's no mechanical work. All right, the boundaries are not moving. And also, if there's like no moving parts, right? So you can't really have any shaft work. If there's no electrical currents that are crossing the system boundary. Cross system boundary. Okay? And so, when you're reading the problem statement for your, material and energy balance problems, try and look out for words that, imply any of these things, and that will help you eliminate terms in your energy balance.